All right, so when comparing a categorical variable to a quantitative variable, this is when we're going to try that Way Anova deal out. But first thing I would probably do if I were looking at something like this is I might do some summary stats. So let's say, which categorical variable is fun? Let's look at units taken, and let's see if the class that someone is in influences their units taken. Because we may think that someone in a hybrid class or an afternoon class, not afternoon, but not 7 a.m. class is taking more or less units. There might be some difference in units. Who knows? So I'm looking at units grouped by class. If I compute this, I'm going to get out the sample size of each of my different classes, and along with a mean, min, max, all that good stuff for my different classes this semester. So it looks like that Thursday class has the most average units, while Tuesday has the least average units. Every class has someone with 3, and some poor soul has 26 units in my 7 a.m. class. I don't know who you are, but if you survived this semester, hats off. I could not have done it. So anyways, when I first look at this, I might go, is that a big enough difference? Is a 1 unit difference going to be statistically significant? I'm not feeling very confident in this, but let's go ahead and do the rest of what we want to look at. So next, I might look at a graph, a box plot. This will allow me to, again, look at the units taken and choose to group by what class people are in. And if I want, I can play around with having outliers or not, drawing the boxes horizontally, putting the mean and medians in there. I can have all the fun I want. So we can look at our 3 different classes and say, yeah, those boxes look pretty dang similar to each other. Maybe the Tuesday box is the small, kind of the furthest to the left and a little bit smaller, but they look pretty dang close. So if I want to quantify that statistical evidence that doesn't seem to exist, well, I would do my Way Anova. So in statistics, down in Anova, you're going to select one way. Now here's the deal. You don't want to compare columns. That would be if you had a bunch of different groups and their data was in there separately. Since all of our data for units is in a single column, that's what we're going to choose. So our responses are the number of units people are taking, and our factors are what class they're in. So my quantitative and my categorical, that's how it will always work. And you're always going to want to choose this because that's the way we have our data set up. And that's really all you need to do. You'll notice there is actually a little checkbox here. I'm just going to leave this in here. One of the requirements for Way Anova, as we noted in the last the video that had all the different tests in it, is to make sure that all the variances are the same. So you can do this test to make sure the variances are the same, to make sure that you're not getting into any trouble. So I'm going to compute this. All right, according to our Anova, we can see again those different means. We got a p-value of 0.45, 0.45. So based on a significance level of 5% or even 10%, this is a terrible p-value. We would fail to reject the null, and we'd have to say that there's not enough evidence to say that these averages are different, right? We don't get to conclude they're the same, but we don't have enough evidence to say they're different. And that's pretty much what we expected just looking at the summary stats. Just a note, looking down here at this test that you don't need to do, but this p-value being large is actually good because we wanted to say all the variances were the same. And so the best we could do with any of these tests for homogeneity of variances is to fail to reject. We actually, if we rejected here, that would mean that Anova is not a good thing for us to be doing. We should be doing some other type of analysis because it's obvious that our standard deviations are really, really different. Now, if you wanted to look at one where we do get statistical significance, we could do a Way Anova, and we could do something like haircut. Oh shit, I need to go to this one, sorry. Haircut, right? How much students spend on a haircut versus gender. We know that this has got to be statistically significant. A lot of people looked at it for that discussion board back in the day. Nobody had a p-value because we didn't know about p-values yet. And I'm going to, again, do that test for homogeneity of variance. Because another thing we saw in the box plots for haircut versus gender was that the women had a way bigger spread than the men. So here's where I think we might get in trouble with our variance assumption. So we're going to press compute. Obviously, we get a low p-value here. The average amount spent by a woman is 42. The average amount spent by a man is 21. But you can see here our test for homogeneity of variance. Ooh, that's terrible. It's a really small p-value, which means our variances aren't the same, which means we violated one of our initial assumptions about doing ANOVA. So this is actually one where we tackled this question for an old data set using t-stats. Since gender, we only have male and female in our survey, we're able to do this two sample instead. So we'll say, okay, this is a bit of a pain in the ass to do for the two sample, but we could look at haircut as long as gender equals female, okay? And then we could look again at haircut whenever gender equals, oops, two equal signs is not right, male. So this is just because the way we have this set up, we don't have those two samples in two different rows. So we actually have to say, grab the females from the haircut sample, grab the males from the haircut sample. And we don't want to pull variances because we can't say the variances are the same. So here's a big advantage is I'm able to, in this two sample T, say like, the variances aren't the same. So I'm able to actually meet my requirements. I have big enough sample sizes for men and women. I'm actually good here. And then I could, again, do a hypothesis test. And the other advantage to doing a two-sample t-test in this case is that I can actually choose a direction. I think women spend more than men. That was an initial assumption I had. So if you have two samples, you can do a little bit more and you don't have as strict of requirements in order to do a two-sample t-test. So if you just have two options, this is another way that you could do this. And then you can, again, we're still getting a small p-value. We're still saying that there's definitely a difference between the genders, but we don't have that big caveat of, except we didn't actually have the assumptions required to run ANOVA. So there you go.